Hello, students. So this is the second lecture on the topic of convergence of series. And we have a few tools that allow us to study the convergence of series. We have the geometric series test, which tells you that the geometric series converges. In fact, it tells you what the limit is. We have the telescoping series test, which tells you that telescoping series converge to zero. Nope, telescoping series converge. But there are many, many more series than that. And what we'll establish in this is some fairly robust tools which can be used to show that a series converges. They won't tell you what the series converges to, but as we've seen, because of sequences, that's a useful sort of thing to be able to do. And an important ingredient in this will be the following result from homework. If you have a sequence of numbers, so that sequence of numbers converges with absolute value bars around the terms, that is, if that series converges absolutely, a sequence cannot converge absolutely. If a series converges absolutely, then that series converges, and this is just saying that same thing again. Now this is useful because let's think about this. Let's think about things like that. Let's start to think about series of this form. And let's think about their sequences of partial sums, and we'll think informally to the side right now. So let's consider the sequence of partial sums, Sn, for a sum of absolute values. Let's compare that with Sn plus 1, namely the sum from k equals 1 to n plus 1 of ak. Well, if you look at that, that's the series that has the first n terms, and then it has that last term. But if you look at this piece, it's positive, or well, I guess non-negative. It could be 0. So that means that this must be at least as big as that. So what does this mean? The sequence of partial sums is increasing. There's the first claim. Lemma 2.10.1. Let AK be a sequence of numbers, then the sequence of partial sums, given by the sum from k equals 1 to n of absolute AK, is an increasing sequence. And the proof is off to the side, so let's just go through the motions. So let's start with just all the setup. Let an be a sequence of numbers. Let Sn be the sequence of partial sums for the infinite series of all of the absolute values. I need to show that this sucker is increasing, so I need to show this inequality. So let's just proceed by expanding. Sn plus 1 is given by the sum from k equals 1 to n of absolute ak, n plus 1. But that's exactly the same as the sum from k equals 1 to n of absolute ak plus absolute ak plus 1 by the definition of Sn and by pulling out that last term. Oh, but check it out. This is exactly Sn. And then there's this last term. Since Sn is the sum k equals 1 to n of absolute ak. Now, this piece is positive, or at least non-negative. Absolute ak plus 1 is non-negative by assumption, so that means that Sn plus 1 is at least as big as Sn. So that means the sequence Sn is increasing. Why does that matter? We know things about increasing sequences. Increasing sequences converge if and only if they're bounded. So if we want to know whether or not this series converges, all we need to do is demonstrate an upper bound. If you want to show that a series of positive terms converges, all you have to do is show that that series is bounded above. Oh, well, that's often easy to do. Here's one consequence of this. So let's let AK and BK be sequences of numbers. Fix some starting index big N. Let's suppose that the absolute value of AK is less than or equal to BK for all K bigger than this threshold value big N. Then, here are some conclusions. If this series converges, then that series converges. If this series diverges, then that series diverges. And let's just stare at these two. These two statements look pretty similar. If this converges, then that converges. If not that converges, then not this converges. So the second is just the contraposition of one. We only have to prove one. This isn't just me being lazy. That's just logic. So let's do that. So setup. Let's let AK and BK be sequences of numbers. Let's suppose that there is some threshold value big N such that the absolute value of AK is less than BK for all K bigger than N. Let's make the hypotheses match up. I will assume that the series associated with BK converges. Well, let's do that. Let's go. So let's let Sn be the sequence of partial sums associated with absolute AK. So Sn is the sum from K equals 1 to N of absolute AK. And let's let Tn be the sequence of partial sums associated with BK. So Tn is the sum from K equals 1 up to N of BK. Now I know that this series converges. So this series converges. That must mean that this sequence, the sequence of partial sums associated with that series, converges. So that means that the sequence Tn converges. Now the difference between Tn and the series you would get if you started not at the first term isn't so hard. Like, those two things are super related. So let's just write that down. So Tn, well, by definition, Tn is the sum from K equals 1 to N of BK. Now I can break this up a little bit, provided that little n is bigger than big N. Maybe I'll put that here. Provided little n is bigger than big N, we get the sum from K equals 1 to N of BK can be written as the sum from K equals 1 to N, big N minus 1 of BK, plus the sum from K equals big N to little n of big K. So let's just analyze this a little bit. So let's focus in on this last term. So the sum from K equals big N up to little n of BK is the same thing as the sum from K equals 1 up to little n of BK minus the sum from K equal to let's see, it looks like to get that I just want to subtract this to the other side. And sum from K equals 1 up to big N minus 1 of BK. So let's check this out. This converges. That's an assumption. So because the sum from k equals 1 up to little n of bk converges, and, well, remember, n is the thing that's going to infinity. Everything else you can treat as a constant. So this is just a constant. The sum from k equals 1 to big N minus 1 of bk is constant in n. It follows that this thing should converge. It's a convergent thing minus a constant. I even know what the limit is. The limit should be the limit of this minus this constant. It follows that the sum from k equals big N up to little n of bk converges. In particular, this sum is bounded. Right? Convergent sequences are bounded. In particular, the sum from k equal to big N up to little n of bk is bounded. Let's let u be an upper bound on that sum. I'm going to use that to establish an upper bound on Sn, which, if you'll recall, is the sequence of partial sums associated with the series of absolute AKs. So let's do that. So just by writing it out by definition, Sn is this. By breaking it up in the same way as we broke up Tn, I can write the first n minus 1 terms and then the last terms. That is now less than or equal to this, which is constant. Well, for every k that's big N or bigger, absolute AK is less than or equal to bk. So that means I can replace this with the sum of bk's and make the whole thing a little bit bigger. Remember, I just want to get an upper bound, and now that I have this in play, I can use that big U is an upper bound on this. So whatever this is, it's less than or equal to big U. Oh, but check out this last line. Are there any little n's? Oh, since U is an upper bound on the sum from k equal to 1. Nope. That final line is something that's constant in big N. So we've shown that for every natural number n, this number is less than or equal to this number. That every term of this sequence is less than or equal to this number. So, that tells us something. That tells us that the sum from k equals 1 to big N minus 1 of absolute AK plus big U is an upper bound on Sn. Oh yeah, and I guess that really this is only for every little n bigger than big N. Right. That was the only way that this comparison worked. But, I mean, how many little n are there that are less than or equal to big N? There are only finitely many. So by the standard argument, I can now conclude that Sn itself is a bounded sequence. So by lemma 2.1.10, which says that Sn is monotone, the sequence of partial sums Sn is monotone. Oops, why is that red? Oh, wait. So that means Sn is bounded and monotone. So by the monotone convergence theorem, this sequence of partial sums, Sn is convergent. And you know what? Let's write it this way. Converges, not is convergent. It's the same thing. Since the sequence of partial sums converges, it follows that the sum from k equals 1 to infinity of absolute AK converges. Notice didn't tell you what the limit is. Okay, so let's use this to achieve something. So here's a claim. The sum from k equals 1 to infinity of 1 over 2 to the k plus k converges. I'm not going to say where it converges, I'm just going to say that it converges. So I'm going to do this by using the comparison test. So reading what the comparison test says, the comparison test says, so here is a thing that we want to show converges. So there's something that concludes that this thing converges. If I can find another sequence bk so that this inequality is satisfied, not forever k, but eventually, then I conclude what I need. So let's try to do that. So in order to use the comparison test, I need to find some other sequence bk, which satisfies that for every k, well, there should be absolute value bearers around this term, right? But that term is already positive. Such that for every k, this is less than or equal to bk, and so that the sum of bk's converge. So let's just look at that. What can I do to that which would make it bigger, but preserve the converginess of the series? Well, one option is I could just go ahead and erase the k, because then I would get 1 over 2 to the k. That would be a geometric series. I know geometric series converge. So let's take bk to be 1 over 2 to the k. Then by the geometric series formula, the sum of bk's is the same as the sum of a bunch of 1 over 2 to the k's, converges. And you might say, well, I even know where it converges. I don't care. There is a formula for that series, but it won't be relevant. So now let's consider any k in the natural numbers. I need this inequality, but that should be like super easy, right? It's just because I've erased that k, which makes the denominator smaller, which makes the whole thing bigger. So let's just write down those steps. So let's see, because k is a natural number, I know that k is bigger than 0. So 2 to the k plus k is bigger than 2 to the k, which in turn is bigger than 0. Thus, one over 2 to the k plus k is in fact strictly less than 1 over 2 to the k, which is bk. Thus, by the comparison test, the sum of a bunch of things that look like 1 over 2 to the k plus k converges.